We'll wait for 5 minutes and after that we'll start. Okay, so let's get started. Okay. Welcome to week 5. So till now we have discussed mostly about primary protein sequences, what things can we infer from those sequences in terms of hydrophobicity, in terms of when you do sequence alignment with multiple other species, you get to know about the divergence or convergence due to evolution and so on and so forth, right? So today our focus is mostly on secondary structures, alpha helices and beta sheets, and how you can like predict protein structures from the sequence. Again, this is not as you are already probably aware that last year a Nobel Prize was given out for predicting the structures, different protein structures using their sequences using something called AlphaFold, which is basically a deep learning model which kind of predicts protein structures from sequences, right? So we are going to learn about some early methods used to do this. So now we have deep learning and other machine learning stuff. So probably these methods are not so widely used today, but yeah, these are important methods. So let's get started. Okay. Okay. So yeah, as I was saying, that we are transitioning from the primary structure, which is the basic amino acid sequence, to predicting and understanding secondary structures, right? Here comes the concept of like when you're going to compare it to other sequences. So one very uh, easy way to predict a structure is basically you take your sequence of amino acids and you kind of align it with all the set of proteins that are there with their sequence of amino acids, and if there is very high similarity between two sets of sequences, it is possible and it is highly probable that these two have similar structures, right? Because the residues at different positions of the protein, the amino acid residues at different positions of the protein, will kind of uh, are responsible for protein folding and different secondary structures that it goes on. So we need a non-redundant data set for that. So what is a non-redundant data set? It's basically if you are using a large-scale data set or a large-scale data analysis, or you're doing up some prediction, so you build this non-redundant databases. What it is basically, that if you have some information in the database, you do not want it to repeat. So the idea is that if you have a particular protein sequence of amino acids, if another set of proteins are very similar to those to that sequence, you do not use that. You use a non-redundant sequence which does not have multiple copies in your database. So the idea is that you reduce statistical bias in any computational analysis or structural prediction. Therefore, it is important. So one example of that would be, so for example, if you have this kind of a sequence of protein, so where alanine is present 4 times, so it would be like 4 out of 20 total amino acids present, and it appears twice alongside this particular sequence. So if the dataset's average alanine composition jumps from 0.23 jumps to 0.23 instead of 0.2, right? So artificially the frequency of a particular amino acid can be increased if you do not have non-redundant data sets. If you have redundant protein sequences, the amount of amino acid in each of those sequences, you do it for the whole data set, right? Whole database, right? So how much of alanine is present, how much of proline or glycine is present. So if you have very similar sequences in those databases, the 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 composition of the different amino acids would be increased artificially, which you do not want, because that would bring about uh, uh, statistical that would bring about statistical bias, right? So if you have a amino acid sequence, uh, we discussed this in the last class, and also I think the class before that, that you can predict the hydrophobicity profiles of different regions of the sequence of the protein, right? So if you have we have different scales for this. There are experimental procedures that you can measure hydrophobicity by. So either you try to you use water as a solvent, and then you use any organic solvent, and then you see the difference in terms of the amino acid getting solved in those solvents, right? So that is the experimental way of doing that. There are computational way of doing that. We discussed about Kite Doolittle scales also. So these are all relative scales, right? So it will tell you the hydrophobicity or the hydrophilic nature of the amino acid with respect to other amino acids, right? And if you have a combination of hydrophobic amino acids and hydrophilic amino acids in a set of residues in alternating manner, it would lead to amphipathicity. So we discussed this last class also, that like it is not a fully hydrophobic region or a fully hydrophilic region. There is a mix of both, right? So that brings us to the amphipathicity part, right? Where you have periodic alternating pattern of polar and non-polar residues in the sequence, right? Okay. Okay, so also we talked about these two things as well in terms of sequence patterns and motifs. So you have specific notations where you can use a set of amino acids describing a particular protein sequence, but you can have variability in the sequence as well. So for example, at a particular position you might have a set of residues in any one of the set, right? So we can use this kind of syntax to show that. And also we also talked about PSSMs, sorry, which are profiles constructed by taking multiple sequence alignments to calculate frequency of residues at every position. This is also going to be biased if you do not have non-redundant databases, right? So if you have all redundant sets, the frequency of a particular amino acid would be artificially increased, which actually is not good for your analysis, right? So here comes the concept of sequence identity. We have talked about sequence alignment, so where we are trying to align a particular set of sequence of amino acids to a larger sequence or a similar protein in other species other than humans. So that we have done. So from that also you can calculate the sequence similarity. But the idea is that the identity of two sequences is calculated as the number of identical residues divided by the length of the shorter sequence, right? So if you have two sequences which share 6 identical residues, out of say for example both of them are 10 residue length sequences, so the identity is 60%. If one sequence length is 12 and another sequence length is 10, we consider the sequence with the shorter length, which is 10, right? So, and if it is exceeding a certain threshold, if two sequences are, say for example, 60% identical and you have put a 40% threshold, then one sequence is retained as the representative data point and the other is removed to eliminate that bias that we were talking about, that if you cannot have very similar sequenced proteins in your database, which is which is bringing in this bias. So when you talk about sequence identity, so you have set of identical characters and basically uh, the minimum length of the two sequences, or also you can talk in terms of alignment. So length of the aligned sequence, how much of the sequence has been aligned, that also you can use instead of the length of the minimum sequence as well. So both of them are kind of used, right? Now, what do you mean by similarity of two amino acids, right? So we define the distance parameter in terms of similarity, right? So if you're given two protein sequences, say 100 residues length, you are asked how much similarity is there between them. So you do an alignment, or you just match one to one, and then you see how many amino acids are matching and what is the minimum length of the two protein sequences, and you can get the similarity. But when you're talking about the distance, you are talking about in terms of in a more qualitative manner. Now first, in a quantitative, we'll come to the quantitative part, how you calculate distances, but in a qualitative manner, it is basically how far away, how diverged two particular sequences of protein are. So if this there are different distance matrix that we use to calculate this. We'll talk about it in the subsequent slides, but this is the general idea that when you calculate similarity, you just see how much is matching, and when you calculate distance, it's basically how much of the two sequences are mismatched, and you quantify that mismatch with respect to different parameters of sequence, the distance. But the idea is, more the distance, more diverged two sequences are, less is the distance, more similar two sequences are. So qualitatively, it is quite intuitive to understand, right? Okay. So yeah, again, this is an example where you calculate similarity versus the distance. So if you're given a string and a target, and you are asked how much similarity is there between the two sequences, or how much distance is between them. So for similarity, only there are two mismatches, rest of them all are matching. So it is basically 8 out of 10 residues that are matching, which is 80%, right? And the other possible parameter that we can use to describe this is the distance. So one such distance is the Hamming distance, right? The Hamming distance is basically number of different positions divided by the total number of total number of aligned length of the sequence, right? So it is kind of the the complement of the similarity, right? So for similarity, it is 8 positions out of 10 matching, so 80% similarity. And in case of Hamming distance, 2 positions are not matching out of 10, 20% is the Hamming distance between the two sequences. So it is kind of complementary to each other, right? There are other distance parameters also we'll talk about, but the general idea is that how much of the two sequences are matching, that will be the similarity. How much of the two sequences are diverging, you can quantify that using distances. One such distance is the Hamming distance, right? So I think it is quite intuitive in nature, right? And one thing is basically the similarity, as I said, we can define it as the minimum length of the two sequence. But for Hamming distance, generally we assume the sequence length to be similar, and if not similar, we assume the length of the shorter sequence as well, in this case as well. So both of them are both of the parameters are very similar in nature, in terms of the calculation and in terms of the information that it is giving you about the sequences, or more than two sequences that you are looking at. Right. The other distance that we talk about is basically the edit distance, which is also uh, known as the Levenstein distance, right? It's a paper that came out in 1965. So they define this particular metric for distance between two sequences. So the edit distance is basically the minimum number of edit operations that is needed to transform a particular sequence to the other, right? What is the level of edits that you need to do? It can be inserting indels, it can be substitution, it can be a gap, it can be any of the things that we have used in alignment, right? So what is the minimum number of edits that is needed to be done to convert one sequence to other, is the edit distance of of the one sequence with respect to the other. So for example, you take these two particular strings, so you have to convert this string to this, right? So let's start with with the first substitution, you substitute the T with a G, because the second position is a G. So okay. Yeah. So you first use a substitution, you convert a T to a G, then you do a deletion and you remove this particular C, then you insert a T at the beginning, then you insert again another T between GA and AT. So you needed 4 edits to convert this particular sequence to this one. You can use other techniques of editing as well. So for example, in the second case, you're first inserting a C between CA, sorry, no, sorry, you're inserting a G, not a C, between TA and CA, T and AC, sorry. So at the second position, you are inserting a G, and then you're substituting the C at the fourth position to a T. So in this case, you did only one insertion and one substitution, and you could move from one sequence to the other one. And this is the third one, is another way of substituting and doing insertions, deletions to move from one sequence to other. Out of the three, the lowest is for the second case, where you can do just 2 edits, and you move from one sequence to another. So as edit distance is defined, it is the minimum number of edit operations. So out of the three, the second one is chosen, and basically it is defined that between S and T, the edit distance is 2, right? Because that's the minimum. So we talked about similarity, how if you have two sequences, how many residues are similar in the two sequences out of the total number of sequences. Then we talked about Hamming distance, basically how many dissimilar sequences with respect to the total number of sequences, and basically the edit distance, how many edits you can do from with one sequence to get the other sequence, and the minimum number of edits. So that is the edit distance. So I think these are the basic distances, and these are the basic parameters that you need to know and understand, because these are the very basic distance matrices or matrix or similarity matrix that is defined in bioinformatics. So if you delve deeper, you will find these things scattered along in a lot of things in the field. So I'll suggest a little bit focus on these kind of very basic things, which will help you understand more complicated things in the future as well. Okay, so again, as I was saying, it is the as I was saying that you are looking for a series of operations of minimum length. So in terms of edit distance, we are looking at, like, basically there can be many ways to edit one sequence to get the other, but what we are trying to do is basically find a minimum of such number of edits that is required. So basically that is what is getting defined here, that it is the minimum of S, which is S is a series of operations which transforms S into T. So yeah, this is fine. Now say for example you have this distance metric, whichever you are using, say for example an edit distance or a Hamming distance, or you're using the similarity metric, like whatever you are using, you have been given a set of say 100 proteins and their sequences, and you are asked to cluster this 100 proteins into 5 different clusters based on the similarity of these set of proteins. Now how would you do that? So I think I mentioned k-means clustering briefly in some of the earlier classes, but k-means clustering is a very good algorithm to do this kind of supervised clustering, right? So here the case is that you are clustering this set of proteins, this set of 100 proteins into 5 different clusters based on their similarity or distance or whatever, based on some parameter that you are defining. So let us, for example, talk about that that we are clustering based on similarity. So the idea is that in one cluster, the set of proteins that will be present are going to be more similar to each other than they are similar to other clusters. I hope I am making myself clear. If you are facing any problem in understanding, please let me know. So if you the idea is that all the proteins in one cluster, when you're clustering say 5 clusters, so all the proteins in one cluster, the sequence of the proteins in one cluster must be very similar to themselves compared to proteins in other clusters. So that is how the clusters are defined, right? So what you're doing is you're partitioning the whole data set into n observations, and n will be defined by you. Uh, sorry, of n on observations into k clusters. This k is defined by you, right? Like some understanding of the biology or the set of data is required to say what should be the ideal k in this set. But like, yeah, you can randomly assign it into k clusters. Now that k can also vary, so you can do it like you might have a hypothesis that these set of 100 proteins might cluster from k equal to 4 or to k equal to 10. You do not know what is the ideal clustering between these set of k's. So 4 to 10 you do not know, and you need to find the best possible clustering. So what do? Firstly, you define k. So you start with k. So for example, k equal to 4. So what you do is you take all those 100 proteins and randomly divide it into 4 clusters. Randomly, nothing to calculate, nothing to worry about. Just randomly distributed into these 4 or 5 clusters. Now you calculate mean values for these clusters, right? What is the mean? The mean would be based on the distance metric that you are defining, or the similarity metric that you are defining. So that is the parameter through which you are doing the clustering. So you calculate the average values. In this case, the values are your distance or your similarity matrix, and you calculate mean of these clusters. Now, uh, so the idea is that when you had first divided into 5 clusters, you had calculated one mean, right? So randomly you have divided into 5 clusters, you have calculated one mean. Uh, Now you calculate the actual mean of these set of protein sequences that you have in a cluster. Now this mean and the mean that you had assumed before clustering, this will have a difference, right? So whatever is the set of protein sequences that are closer to your current mean, you keep in the cluster, and then you remove the rest of the elements from the cluster, and then you try to put those elements in other clusters from which it is closer to their mean. So uh, I'll just try to write and explain. If I think I'm like just saying it is not very clear, so I'm going to try and explain while writing, right? So uh, say for example similarity. This is so if you want to make a plot like this, where you have the similarity score on the x-axis and number of protein sequences on the y-axis, so this will become something of a histogram, right? So say for example at point 2 similarity, you have 500 individuals. At point 3 you have 300. Point 4 you have this many. I'm just randomly drawing, right? Say point till goes to point 8. Now the values on the y-axis is telling you basically the total number of protein sequences, and this is the similarity score, right? So for example, for point 2, let us assume this is like
Sir, we are not able to see the full page.
there is nothing written on the full page, like just the top part. Can you see?
No, no, I was not able to see the whole graph. Now I can see.
Now it's fine. I'll just move it a little further. It's fine now.
Yeah.
Yeah. Okay. So what you're doing is basically drawing a histogram, right? So here is your similarity scores, and here is the number of protein sequences with that similarity score. Now this is the data that you are given, right? A set of proteins, a set of you have calculated similarity scores between this set of proteins, or whatever edit distance or Hamming distance or whatever and whatever, and this is the data that you have. Now you are asked that based on this information you have to cluster this set of proteins into 5 different clusters, right? So what you do is start by randomly assigning 5 clusters. So I'll start, I'll assign the first cluster somewhere here, the second cluster somewhere here, the third cluster somewhere here, fourth here, something like this. So this is one, this is one, this is one, and this is one. Say we are doing 4 clusters, right? So randomly you're dividing it up into 4 clusters, just based on a set of similarity scores. You're just randomly, there is no need that these set of proteins should be in one cluster. You can take these and this and the last one as one cluster as well, because you're doing it randomly, right? So if you do it like this, so the idea is that now you have randomly divided into 4 clusters, but this is not the best clusters possible, right? You have to do an iterative algorithm, an iterative calculation of mean to see if these are the best clusters or not. Now what you do is you have randomly divided into these clusters. Now you calculate the mean of these set of values. So the value of the mean will be somewhere, I'll write it here. So this will be M1, M2, M3 and M4. The means I have written it like this. So M1 is the mean of this cluster, M2 is the mean of this cluster, M3 is the mean of this cluster, M4 is the mean of this cluster, right? Now what you do is, from M1 is a value, right? So you check what is the distance between M1 is the mean, and the set of protein sequences that is present in the first cluster, right? Then you do the same thing for the second cluster. M2 is the mean. Now how much far, like what is the distance between this set of proteins from M2? What is the distance between this set of proteins in this cluster from M3? What is the distance from this set of proteins from M4 in this cluster, right? Now what you'll do is you are recalculating the mean, right? So what you are trying to do is, so for example, for M1, so it says, right, you're calculating it like this: total similarity by the total number of proteins present. Now what you do, so for example, there are P proteins in M1 in the first cluster, right? So P1, P2, P3, say for example P goes to Pn, n set of proteins that you have from M1. Now what you do is you calculate the mean of this, right? You have a previous M1, now you have another set of values in M1 from which you can calculate the mean. So the idea would be the mean of this, so let me write it like this, M1 dash. So you have calculated M1 dash from all the sequences that you have randomly assigned, and M1 is basically the mean that you have assumed in the first place. So what you calculate is basically M1, M minus M1, M1 dash, whatever. The idea is that this needs to be reduced. This needs to be optimized. So the optimization problem is that minimize M minus M bar. This is the optimization problem. If you think about it, when you're clustering a set of proteins together, the idea is that these set of proteins are very similar in nature or very different in nature, whatever metric you're using. Let us assume that you're using similarity. So these set of proteins are very similar in nature. So the mean of this set of proteins, similarity score, and the mean that you have assumed while doing the first random division into clusters, those means should be very close to each other. That is the thing you are trying to optimize. So what you do is for you're trying to minimize this, right? So if a particular if a particular protein actually is uh, say for example, let me do it like this. Right. So this is your M1 set. Now what you have done is in your M1 set also you have another another set of proteins, which is like in terms of, since you have randomly assigned, you have a random set of proteins which are very high in similarity score compared to the rest of the set of proteins, and that protein is also randomly included in your first cluster. So the idea is that this particular set of proteins will stand out when you are doing this thing, right? When you're trying to minimize uh, the sum of squares or whatever. So this particular set of proteins will stand out because these will have much more similarity scores compared to this. So this will be taken out from this particular M1 cluster and will be put to a cluster which is closest to it. So if the mean of this set of proteins is, say for example, m uh, so m2, let us just say this is m2. So m2 will be assigned, so m2 is for all the set of proteins, so m2 will be assigned to cluster kn if the the value of the mean of kn is closest to m2, right? So I think I might have little bit made it a little bit complicated, but the idea, just the general idea, is that you have a set of variables. You are randomly assigning them into one cluster, and you are seeing how much the mean is changing from the random clusters you have assigned to the actual mean of the set of protein sequences that you are attaching to one cluster. So based on the differences, you calculate this particular thing within cluster sum of squares. So within cluster sum of squares is basically from the mean how much is the divergence in terms of similarity. So that you calculate for each set of proteins, and you use sum of squares for this because it can be negative as well. So you use sum of squares, and the idea is that you try to minimize this sum of squares. So you do this iteratively. You take out one set of proteins and put it into another cluster based on their mean, and so on and so forth, and you do it iteratively for a large number of times until your mean does not move. So until in the next iteration also your mean is the same, and in the further iterations also your mean is remaining the same, it is not changing. So at that point of time you break the iteration and say that this is the best set of clusters that we have got, right? So the general idea of k-means clustering is it's a supervised clustering algorithm where you have to have an idea about how many number of clusters you want. You might want a range of clusters, like you might want from 4 to 10. What you can do is, if you do not know what is the actual set of clusters that is going to be possible with this data, you do from 4 to 10, and then you take the one with the minimum set of divergence, like minimum sum of within sum of squares, right? That is the optimization problem that we are looking at, and it is this thing that I said. You're trying to minimize this. It is basically the same thing within cluster sum of squares. It's basically difference, and you square the difference so that you do not have negative values. So for k equal to 4 to k equal to 10, which k has the lowest within cluster sum of squares will be the ideal k for your data, right? So I hope you have understood a little bit, because k-means clustering is something that if you're doing bioinformatics or computational biology in the future, or any kind of data science, data analytics, machine learning, whatever you are trying to do, k-means clustering is a very basic algorithm that you will need to understand and need to know. So I hope I could have given you an intuitive idea about how it works. The mathematics is very simple for k-means clustering. It's just calculating mean and seeing how much the mean is deviating from each of the cluster, right? to say anything?
Yes, sir.
Yeah, yeah. Go on.
So, when we are forming the cluster, so let's say 4 to 10 years ago, so there are specific number of sequence assigned to that cluster. So, if I'm
Nah, so say for,
taking cluster number 4 and assigning 5 amino acid sequence. So,
so the number of clusters that you want. So say for example, you want 4 clusters, right? In the first step, the initiation of the k-means clustering is that you randomly assign all your data into 4 sets, right? That 4 sets, you do not need to do any calculation for that. You just randomly take a set of data points and you put it in one cluster. In the next iterative state, what you do is basically you check is actually the mean of these set of proteins that you have put together in a cluster, are the mean of these set of protein sequences similar or not. That is what you are trying to ascertain with repetitive iterative processes. So the idea is that you first randomly assign it into set of 4 or 5 clusters, whatever the k you are working with, and then you try to refine these 4 or 5 clusters based on the distance between the mean of that whole cluster and the sequence similarity of a particular protein. So yeah, so the basic idea is that first you're doing
yes.
dividing it randomly,
Okay,
then
so
you're refining it with every iteration, and you stop at that point where your mean is not changing. That means that is the best possible clustering for at least that particular k. That is the best possible clustering possible, right?
okay, sir.
Yeah. Okay. Yeah. Please. I would suggest read a little bit on k-means clustering and other similar algorithms like hierarchical clustering and so on and so forth, because these are very common algorithms and it may help you in future as well. Now, once you have formed these clusters, whatever number of clusters are, uh, once these clusters are locked, a representative sequence are pulled from each cluster to form a non-redundant database. Now, can you connect the link between non-redundant database and this clustering part? See, the k-means clustering has given you 4 or 5 clusters. Now, these clusters contain protein sequences which are very similar in nature, right? Because that is how you're measuring the that is how you're using the distance matrix. So if protein sequences are very similar in nature, they will be present in one cluster. Now, when you are making non-redundant databases, you do not need redundant information. Now, proteins in one cluster will be very similar to each other, so the information there is very redundant. So what you do is you take a representative sequence out of this particular cluster, which is actually representing most of the proteins in that cluster, and you use that for to form a non-redundant database. Because if you use all the proteins in the cluster, it will be redundant because they are by definition very similar to each other. So to tease out this similarity and build this non-redundant database, k-means clustering is a very good approach to do that, because what you're doing is basically clustering the proteins based on their similarity and then picking the best possible representation of these set of proteins in that cluster to form the non-redundant database. Right. Okay. Okay. So I will talk a little bit about these other set of software tools, algorithms that is used to calculate sequence identity, similarity, and dissimilarity, and so on and so forth. So CD hit is one of them. So I looked into the website of CD hit. It looks like the program was last updated in like 2014, 2015. So it's been 10 years. The program has not gotten any update, but the algorithm is quite interesting. So yeah, CDHIT stands for Cluster Database at High Identity with Tolerance, right? So what it does, it takes a FASTA sequence. I hope you know what a FASTA sequence is. It's a format where you format of a file where you store sequences, right? So if you do not know what FASTA is, please use Google, and it's a very simple format. You have a line describing the sequence, and then you have the sequence. Then again a line describing another sequence, you have another sequence. So this is how a FASTA sequence looks like, right? Uh, so you take this FASTA format sequence database as input, and you produce a set of non-redundant representative sequences and as output. So this is what CD hit does. So again, from from that particular line you should be able to understand that what this is doing. This is calculating distances or similarities between set of protein sequences, right? Because it is telling you from a set of sequences what is the non-redundant representative sequence. For that you need to calculate similarity and distances between those set of sequences, right? The idea is to reduce the overall size of the database without removing any sequence information by removing only redundant or highly similar sequences, as I was saying. The resultant database will be non-redundant and so on and so forth. So it follows a greedy algorithm, and it calculates this set of similarity matrix, and for 90% identity it searches for shared identical decapeptides, which is like if there is more than 90% identity, it tries to see shared residues at 10 length at a time, right? For 85% the number of peptides drop to 5, and if the sequence similarity drops further it will check for a lower number of residues as well. So it is good for large data set, but it struggles if the sequence similarity is below a certain threshold of 30 or 40%, right? Blastclust is a basically a standalone program inside Blast, which also does kind of a similar thing, and it uses BLASTP to compare pairwise matches between proteins. I hope you remember BLASTP. It is basically sequence alignment of amino acid. So it uses that algorithm to calculate sequence similarity and so on and so forth. So and unlike simple identity, this BLASTclust allows users to specify sequence coverage. Say for example, you can define as 90% coverage or 80% coverage. So how much of the sequence do you need to be covered in your original sequence? So that you can define beforehand. And it also prevents short fragments to be aligned to long proteins from artificially skewing the dataset. And also it can handle lower redundancy threshold down to 20 to 25%. But the general idea of these kind of algorithms, CD8, K-means or BLASTclust, whatever, the idea is to find similarity between set of proteins, try to bring the set of proteins which are very similar to each other in a cluster, and basically create non-redundant databases based on the information of those clusters. So that is the general idea across these different algorithms, right? Now what will this this exercise of doing or calculating sequence similarity or edit distance, Hamming distance, or whatever, what are they going to tell you in terms of the protein itself? So if a particular protein, you know the secondary structure, basically you know the folded 3D structure of the protein, and you know the sequence of the protein as well. Now if another protein is 90% similar to that protein, it is very likely that it will have a similar kind of a 3D structure to that protein itself, right? So comparing edit distances or similarity scores and everything could tell you between two proteins how much similarity in terms of the secondary structure is there as well. So we are going to talk a little bit about the prediction of secondary structures from amino acid sequences, right? So the information in this slide is mostly we have discussed earlier. So the alpha helices, I hope you remember, they are stabilized by hydrogen bonds between the ith residue and the I plus 4th residue, right? And it is like around 3.6 residues per turn, 5.4 angstroms rise per turn as well. And so if you calculate the rise per residue, it is around 1.5 angstrom per residue, okay? So these kind of set of set of hydrophobic residues present in certain regions of these proteins help the protein fold. And when you have transmembrane proteins, you need a lot of hydrophobic residues. So because of this 1.5 angstrom rise per residue, to cross a 30 to 40 angstrom lipid bilayer, a transmembrane alpha helix must roughly contain 20 to 26 closely packed residues. So if you know it's a transmembrane protein, you know that there needs to be hydrophobic residues, and if it's a transmembrane protein alpha helix, because it is like 1.5 angstrom per residue is the length of the helix, so you need around 20-26 residues inside the transmembrane region of uh, of the protein to actually be a functional protein like that. So there can be other variations to these alpha helices. There is three based in helix as well, which is basically a little bit tighter, which has, so the original alpha helix has hydrogen bond between I and I plus fourth residue. In this case, it is I and I plus 3 residue, and for the pi helix, it is a little bit looser on the looser side. It is I and I plus fifth residue. So this is one website where you can go around and play with. So basically, look at different secondary structures and different helices and so on and so forth. It takes a little bit, yeah. So this is the original helix, alpha helix, that we were talking about. This is the 3 base 10. So this is a little bit more packed, and the pi helix is a little bit more loose. So loose and packed, so if it is becoming more packed, it becomes a little bit more elongated, and if it is a little bit loose, it becomes a little bit more shortened, right? So yeah, you can play around this. There are a lot of good information in this set of wiki pages, so if you are interested, please take a look at this. Okay, now coming back. Okay, so that was for alpha helices. For beta sheets, we have discussed again. So you have basically uh, sheets of these polypeptide chains where you have anti-parallel strands, and each of these anti-parallel strands have hydrogen bonds between them, which stabilizes and makes this a sheet-like structure. So you have this set of anti-parallel strands going from one direction to another. This is going from this side to this side, and this is from this side to this side, and it forms these hydrogen bonds, these dotted lines between the two strands of the amino acids. So yeah, so it forms, it can, mostly it is anti-parallel, but it can also form parallel strands and form hydrogen bonding on them, and this becomes a mesh-like structure, a sheet and a mesh-like structure, which gives stability to the protein. Now the thing is, you have alpha helices and beta sheets, but you know what kind of residues reside in different levels of these secondary structures. So for example, in the transmembrane proteins, you know that you need hydrophobic residues. For other cases, you might need amphipathic residues, and so on and so forth. Okay, now approximately one third of the residues in globular proteins are found in turns. They act as connectors that reverse the direction of the polypeptide change, formed by hydrogen bonding between the carbonyl oxygen and the residue of the amide nitrogen of I plus 3. So there are different kind of turns that are possible. We're going to talk this about this in the Ramachandran plot slides, but yeah, just to give you an idea that there can be variations in terms of the folding based on the angles between these different types of polypeptide chains. Yeah, this is just a representation of how the alpha helix and the beta sheets look, and what is the hydrogen bonding pattern of the amino acids between them. Right? Now, uh, generally, the amino acid is formed of your side chain, your carbonyl group, and your amide group, right? That's the basic structure of an amino acid. Now, there are many bonds in the amide backbone of a peptide, and many more in a protein. Uh, I hope you can distinguish between these two. So, when there's just the backbone of amino acids, there will be some bonds that is kind of keeping this. There can be uh, peptide bonds, which is like connecting one amino acid to another. So that is the very basic set of bonds that you have in your primary structure. But when you go to secondary and tertiary structures, some other set of bonds come into play, other covalent bonds, hydrogen bonds, van der Waals forces, and so on and so forth, which kind of stabilize the whole structure of the protein. With all those degrees of freedom, because there are so many bonds present, different types, Um, each bond that can rotate is a degree of freedom. So, uh, if there is a bond, if it's a single bond, it is generally rotatable. If it's a double bond, it generally does not rotate. And if it's kind of a benzene ring like structure, you have resonance inside the ring, it actually forms double bonds, so there is no rotation there as well. So basically you need to have single bonds for rotation. And also, just to recap a little bit of class 12th chemistry, there needs to be space, there needs to be sterically something needs to be smaller to be able to rotate. If you have a very large R group which is hydrophobic in nature, and also the group is very large, it will cause steric hindrance for the rotation. So not every rotation is permitted, right? With all these degrees of freedom, we would expect a near infinite variety of secondary structures in protein, right? Yet we only see only two major classes of defined secondary structures, the alpha helix and the beta sheet. Why is that? Because there are limits on the rotations of these set of infinite set of bonds that are possible, right? We do not have as many degrees of freedoms as we have bonds, because one type of bond in the backbone does not rotate freely. The amide bonds are held in a planar orientation due to orbital overlap between n orbitals of the sp2 hybridized atoms of the carbonyl group and the n orbital of the sp2 hybridized amine group. This distributed n orbital system resists rotation, and the orbital overlap would have to be broken. The distributed nature of the system also makes the amide bond resistant to hydrolysis as well. So again, even if it's a single bond, there are restrictions about rotation, because there are sp2 hybridized atoms, there is resonance, there is like pseudo double bonds and so on and so forth, which actually restricts a lot of this movement, free movement, right? So the amide group will prefer to have all atoms connected to it in the same place as the amide bond with no rotation, and this can result in the cis and the trans conformation. I hope you're familiar with this terminology. The cis is basically present on the same angle, so in the same side of the carbon of the double bond. If it is present, it is called cis. So this is the double bond, this is the bond that we are interested in, the carbon nitrogen bond. Both the R's are present in the same side. In this case, one R is present in this side, the other is present in this side. So this is the trans configuration, this is the cis configuration, right? Note the steric clash between the side chain groups in the cis form. So when you have the cis form, you have these two big R groups which are on the same side of the plane, which causes steric hindrance, and basically is not very good in terms of the stability of the protein, right? So if you just give me a moment, guys. I seem to have spilled water all across. Just give me a couple of moments, I'll be back. sorry for that disruption. Okay. Yeah. So as we were discussing, if you have these two large group of your side chains on the same side of the plane, it causes steric hindrance, and this makes the structure of the protein not very stable. Right. Now you can assume a polypeptide with a planar amino acid bonds which are all in trans, something like this. The the R groups are always opposite to each other. Uh, and you can imagine this as a series of planar structures connected by swivel joints. The swivel joints is basically this particular carbon. So there is a excuse me, there is a carbon here which is connected to both this carbonyl group, which is the CO group, and it is also connected to the NH group, the amine group, right? So this carbon is basically the swivel joint that we are talking about, and this is basically defined as the alpha carbon, right? So the two atoms on each amide bond and the four atoms connected to them are coplanar for each individual amide bond. Any two planar amide groups share a common atom, the alpha carbon of the amino acid residue, which is this one. Now the swivel joints have two connections that can rotate freely, like a universal joint in any machine, right? Now we define how much a particular joint can swivel, how much can it rotate. So there comes the work of Professor Ramachandran in the 1960s. So he kind of defined that these are the set of possible angles possible, and these are the set of angles which are not possible for different kind of combinations of amino acids and different structures, right? So again, we are concerned about this particular carbon, which is the alpha carbon. So on the left side of this is the carbonyl atom, on the right side is the amide atom, and it can rotate on the base with respect to that carbon, right? Now we define two different angles for this. One is the psi angle and the other is the phi angle, right? The psi angle is basically the bond from the alpha carbon to the carbonyl group. So basically this angle, this is the angle that we are talking about. For in case of the psi angle, it includes a carbonyl carbon in a 360-degree range. The angle is measured by looking at the bond with the carbon of the carbonyl group in the rear and the alpha carbon in the front. We measure the apparent angle between the two bonds to nitrogen that you can see coming out of the axis of the alpha carbon and carbonyl bond. So basically this particular bond originating from this carbon and the carbonyl carbon, right? So that is the psi angle, right? This is measured from negative 180 to positive 180 because it can rotate fully, 360 it can rotate, with positive direction being when you turn the rear group clockwise, so that the nitrogen bond is clockwise in front of the nitrogen bond. The rear nitrogen is clockwise, nitrogen bond is clockwise of the front of the nitrogen bond, and the front group counterclockwise to the rear nitrogen bond is right. So this is the angle that you are measuring, and basically this particular carbonyl can be facing towards the side chain, on this particular carbonyl can be facing away from the side chain. Those are the two extremes, positive 180 and negative 180. Right. So this is the sense of rotation that is possible. So this is basically your initial psi angle. Now if you rotate it by 180, so this is your alpha carbon, you rotate the alpha carbon by 180. So this O comes on the top and this particular nitrogen comes down. So this is the 180-degree rotation for that, if you rotate it by psi. Now if you look it from a different cross section, different angle, so this is the alpha carbon, now you are rotating by 90. So this O will come here and this N will come here. So basically it rotates, right? So this is psi equal to 90 and this is psi equal to 90 again. So basically midway between this rotation, right? So basically based on the alpha carbon and the carbonyl bond, the angle between that rotation is known as the psi angle, which is the alpha carbon and the carbonyl bond, right? Now the second type of bond is the psi bond or the psi angle that we are looking at. It is basically with the other bond. So this was the phi bond. Now this is the psi bond. The alpha carbon connected to the N terminus of the amino acid, right? So the bond from the nitrogen at the N terminus to the alpha carbon of the amino acid residue can rotate and turn the whole plane of the other amide group, which includes the nitrogen, in a 360-degree range. It's similar. This angle is measured by looking along the bond with the nitrogen atom in front and alpha carbon to the rear. We measure the apparent angle between these two bonds to the carbonyl atoms. Yeah. And this angle is labeled as psi, which is ranging from negative 180 to positive 180. And yeah, so the positive and the negative is defined based on the carbonyl presence of the carbonyl atom on which side of the group. Right? So yeah, these are the two angles that we are going to be interested in. In Ramachandran plot also, these are the two angles that are used. The values of these two angles are used to tell you if a particular conformation is possible or not possible. So this is the psi angle, which is phi angle, sorry, which is the connection between the alpha carbon and the nitrogen, and the psi angle, which is the alpha carbon and the carbonyl group. Right? Now we come to the Ramachandran plot. Now you can vary both of these angles. But hypothetically, in real life there will be much, like a lot of other factors influencing that. But hypothetically, you can vary the phi and the psi both from negative 180 to positive 180, which is like 360-degree rotations for each. But many combinations of these angles are almost never seen, and others are very, very common in proteins. We'll see the Ramachandran plot in the next slide. We can take basically X-ray crystallographic data, and we can check what are these psi and the phi angles across different proteins, and you can report this set of psi and phi angles for each and every residue of this protein. Now if you do it for yeast, this is how the Ramachandran plot looks like. So a Ramachandran plot is basically a plot between the psi and the phi. These two angles, when you're plotting in a plane, this is the Ramachandran plot. So here you have a set of residues which are negative phi, positive psi. So this set of residues which are both negative, which is in the third quadrant, and the first quadrant, both are positive. But you see the most of the concentration is basically in the second quadrant and the third quadrant itself. There are, as we were saying, that if you see across different protein structures, hypothetically any value, all the ranges of psi and phi are possible, but we only see a particular set of angles, right? So the reason is because of certain bonds that are present in the set of proteins that we are looking at, right? So these atoms take up space and they cannot occupy the same space at the same time, which brings us to steric hindrance. Covalent bonds connect them, and these bonds cannot be broken, right? So the movements that we are concerned with involve rotations only, and we have seen previously that there are only two angles that rotate in a given residue, which is the psi and the phi. But all combinations are not possible due to physical clashes of the atoms in a 3D space. These physical clashes are known as steric interactions, and they limit the available values for psi and phi across different protein residues. So yeah, this is the basic like steric limit that we have for a set of proteins, right? Alpha helices map to a tightly restricted region, which is usually around phi negative 60 and psi negative 45. So phi negative 60 and psi negative 45 would be somewhere here. So these are all your alpha helices. The residues that are basically clustering at this level, this is your alpha helix, while the beta sheets have a much wider allowed region, top left quadrant, due to their extended flexible nature. So basically these are your beta residues, but again, like, they have a much wider range of possible angles. But the alpha helices, as you can see, these are the set of alpha helices. These are very tightly present, and the amount of variation possible is very low, right? Now if you take phi to be 0 and vary the other angle, which is the psi, you'll observe when psi is near to 0, you have a very high steric clash. So in this case, psi and phi both are zeros, but you see the big groups are on top of one another, which is not very structurally stable, right? So if both of them are zero, you have very serious steric clashes between the amide group of the amino acid residue attached to the carbon terminus of the amino acid residue in question, and the carbonyl attached to the N terminus as well. So this is a clash labeled as O1H2 clash for the backbone oxygen, and one residue clashing with the backbone amide hydrogen in the next residue due to the phi and the psi angles, right? So if you have certain angles in for phi and psi, certain values for phi and psi, in some cases sterically they are almost impossible to be present because they'll be clashing with each other. One group will be sitting on top of one other, which is not possible in a natural system, right? So you have these different clashes. So one is the O1H2 clash. So this is the first oxygen and the second hydrogen clash, right? Sorry. Uh, Now, if you have psi as 180, we do not have a very serious steric clashes between the oxygen of the carbonyl atom and the C terminus of the residue and the carbonyl atom attached to the N terminus group. This clash is labeled as O1O2 clash because these two oxygens are clashing with each other. And if you have any value of psi, we have significant steric clashes with the carbon atom of the carbonyl group at the C terminal and the carbonyl group attached to the N terminal. So this particular set of clashes, this is known as O1C2 clash for the oxygen backbone and the carbon of the carbonyl group in the next residue due to the psi and the phi angles. So these are the different set of clashes. So first, this is the O1H2 clash, this is the O1O2 clash, and this is the O1C2 clash. So there are different type of clashes that can occur if you assume different angles for psi and phi, right? So yeah, these are the set of regions where these clashes can occur. So this is the region where O1C2 clash can occur. These are the regions where O1O2 clash can occur. These are the regions where O1H2 clash can occur. So why is it so important? Like, why is Ramachandran plot so important? Why is studying the angles so important? The idea is that you are predicting a protein structure from a set of amino acids, right? And that is not very easy to do unless you know what the structure is, right? So when you're trying to do that, you are going to assume different you're going to come up with different assumptions and predict a protein structure. But when you want to validate it, if the protein structure is even possible or not, you draw up a Ramachandran plot and you see if there are, by your prediction, are there O1C2 clashes, are there O1H2 clashes, are there O1O2 clashes, and so on and so forth. So the idea is that the Ramachandran plot will act as a validation to your prediction. So if certain residues fall in regions where there is high steric hindrance and this is naturally not possible, that would mean that your prediction is not perfect. So it's not a very good prediction. So this kind of information we can get from Ramachandran plots, right? Okay, so moving on from Ramachandran plots, we are talking about something called DPSS, right? So DPSS or DSSP, whatever you want to term it. So the Dictionary of Protein Secondary Structure. It is commonly used to describe the protein secondary structure with single letter codes, right? The secondary structure is assigned based on hydrogen bonding patterns, and this was proposed way earlier than any protein structure has been experimentally verified or determined. So there are 8 types of secondary structures the DSSP defines. So these are the single letter codes GHITEDSC, and these mean different things. So for example, H is a normal alpha helix. If you have G, it is a 3-base 10 helix, which is a little bit more compact. A pi helix for I, which is a little bit more loose. There are other type of helices. There are other type of beta strands as well. So different structures of these secondary structures are given by the single letter codes, right? So if you are interested, please even go take a look at this. This is interesting. So they can you can, as you can write the protein sequence the amino acid sequence of proteins in single letter codes, you can also write the protein structure in single letter codes as well. So yeah, that is quite good. Now when you're predicting the secondary structure of a protein, uh, the idea is that you classify each residue as a particular secondary structure, if it's an alpha helix or a beta sheet or a coil. The assumption is that the secondary structure of a residue is determined by the amino acid at a given position and the amino acids of the neighboring residues as well. And something is defined as a chameleon sequence, which assumes different secondary structures depending on the fold context, right? Depending on the pH of the available medium, depending on other factors, the same sequence will fold differently. So these are known as chameleon sequence, and it generally has around 11 residues which control this thing, right? Now there are different algorithms to predict secondary structures. Initially, there are a lot of statistical algorithms. One of them was the Chow-Fasman algorithm, right? It is basically a statistical approach based on calculation of propensities of each residuum to either form an alpha helix or a beta strand. And it is a low accurate algorithm because, again, you do not have any proof to that. So you're just um, calculating a propensity or a probability of an amino acid to be in a particular structure, right? So it is, the statistics is defined by this. So R is your amino acid, S is your secondary structure type. So F of RS is basically number of times the amino acid occurs in alpha helix or a beta sheet, and NS and N are the total number of amino acid in conformation in the alpha helix conformation or the beta sheet conformation, and the total number of amino acids possible. And this is given, this is the formula for calculating the propensity. So it's a probability form, right? Yeah, now say for example you have a data set with total non-redundant number of residues to be around 100,000. One third of them are in helix conformation, and alanine is observed 8,000 times. So, and 5,000 of alanine are in helix conformation. So how would you calculate these parameters? So F of RS would be calculated as, so how many times alanine is present in helix, which is 5,000, how many times total number of alanine is present, which is 8,000. NS by N is basically one third, which is this particular information. One third of them are in helix formation out of how many number of residues that particular residue is present in that particular conformation. So NS by N is one third. So if you plug in the formula here, you can calculate the propensity, which is coming to be around 15 by 8. Now if you want to calculate propensity across different things, so propensity of a particular amino acid being in alpha helix, propensity of it being in beta turn, or propensity of beta sheets, or the propensity of it being in a turn location. So it has calculated for all the amino acids for all the databases present. But yeah, this is a kind of an older metric to be used, but it gives you a general idea about how, in terms of just the distribution of different amino acids in different secondary structures, you can predict a secondary structure of a new protein looking at a set of amino acid residues, right? So what it does is basically look for stretches of continuous residues with helix propensity at least 1, and you declare such regions as a helix. Similarly, you look for sufficiently long beta regions, and you define that as beta, and so on and so forth, right? Now the idea is that we are looking at one particular residue at a time, in this case in the Chow-Fasman algorithm, but the idea is that one particular amino acid is not responsible. It is a set of amino acids in a sequence that is responsible for it being in a particular secondary structure, right? The idea is that you can look at triplets, right? So you can, if you have like 20 amino acids, if you look at all the possible combinations, it will be like 20 to the power 3 possibilities, right? And you approximate all of these frequencies, all of these combinations, you approximate, and you compute the propensity if A being in helix strand given the knowledge of its neighbors. So you calculate the propensity of A being in a helix strand, which you calculated using Chowman's propensity, but also taking into account the amino acids that is neighboring this particular amino acid. What is the propensity of them as well? So you compute all three. So A of j minus 1, A of j, and A of j plus 1 for alpha helix. For beta also, beta sheet also, you calculate the 3. If it is present in some other window, it is also calculated in 3. You can take a larger window as well. Like, why limit yourself to the 3 residues? Right? You can take a larger window, like 10 or 20 residues. So that is the idea behind this GOR method. So in this case, they consider a window of 17 positions and see how the conformation of the central residuum depends on this residuum and its 80 neighbors, 8 in each direction. Ideally, one would consider all possible combinations of these neighbors, which is impossible. You have 20 amino acids, and if you are seeing 17 positions, it is 20 to the power 17 sequences, which is computationally not very possible. Instead, you assume that the central residuum depends on its neighbors, but the neighbors are independent of each other. And you can use some statistical method derived from protein knowledge of protein structures, and you store it in a matrix of 17 by 20 if you are looking at 17 positions and 20 different amino acids, one for each of alpha, beta, and coil. So you have 3 such matrices that you make, and once you make that matrix, it becomes easy for you to understand. So if that amino acid is present in this position, what is the propensity that it will be in a alpha helix or a beta sheet or a coil, which is the highest out of the 3. And if it is if alpha helix is the highest, that set of residues are supposedly to be present in alpha helices. Now, for the final prediction, you compute for every neighbor x of distance 8 or less. We compute the propensity of a given residue to be in secondary structure of a given type, helix, strand, or loop, under assumption that x is a particular amino acid, and you sum the contribution from all neighbors. Right. So till here are basically statistical techniques that are not very difficult to understand and comprehend, that why you are doing this kind of a thing. But next we have a lot of machine learning approaches, right? So I'm just going to talk about this particular approach, which is the PhD approach, which uses 2 levels of neural network. So this is a deep learning model. So in the I'll not go into very details of the models because that is out of scope of this course. But I would, if you are interested in deep learning with respect to protein folding and protein structure prediction, yeah, this is the paper that you should be reading, and I think John Jumper and Demis Hassabis got the Nobel Prize for this last year or the year before, if I'm not wrong. But if you want to know about deep learning or machine learning with respect to protein folding, this is the kind of the gold standard that we have right now, and yeah, looks like a very interesting paper. You can take a look at that. Okay. There's one question. Okay, if I have a peptide sequence that is derived. It depends. So if I'm understanding correctly, if you are saying that if you just take 2 known peptide sequences and you kind of join them together, and from that information, how can you predict the 3D structure, because there are no like known protein sequences of the similar sequence. Okay, you have 2 known sequences, and you're trying to merge them together and try to predict a particular structure, right? So the idea would be that deep learning models like AlphaFold and other deep learning models, I am not sure about PhD, but these will have enough data to predict what kind of structure it will be. So for example, you are taking these 2 sequences, one from one structure, the other for other structure. What it will do is basically for the left side of the sequence, it will try to predict it, because this sequence is from a known structure, right? So it will try to predict what are the set of residues in this structure, in this set of sequences, which is giving the structure its nature, right? So if those residues can be found, then the structures will be very similar. The left side of the sequence will have a very similar structure to the known one. Similarly, the right side will have a similar structure to the known one. But when you combine it, you will have to look at so these are the two set of protein sequences that you are combining. So at the middle point, at the middle residue, you have to check what kind of residues are there. Say for example 18 to 20 residues at the middle, what kind of structure it is conforming to. So I think deep learning models and current models can easily predict this. I don't think this is a very big deal in terms of the computational and the data power that we have currently. It is not explicitly modeled on one or the other. It is kind of modeled on both. So that is the idea of neural networks, right? So it is not one source of data that you are looking for. You are looking for multiple sources of data, and whatever you learn from those sources of data, you use it to predict whatever, in this case the sequence. So deep learning models, I'm assuming, can do this not in not so like it can do it quite easily, is what I would assume. But again, I have not done anything like this, or I have not seen anyone doing anything like this. This is all I'm talking from an assumption point of view. But I do hope, like I do hope that it can predict based on the neural networks and the data that these models have. It is not very difficult for them to predict a sequence like this. Yeah. Okay. Yeah. So yeah, PhD is an older version of a neural network used for prediction of protein sequences. So there are two levels of this the two levels of neurons that are present in this network. For modern deep learning models, you have like hundreds of layers of these networks, which helps the model to learn better. But in this case, you have two layers. One is basically using multiple sequence alignment, and it is responsible for scoring the residues in any of the three secondary structure based on some method like GOR or multiple sequence alignment or so on and so forth. And the second layer is basically connecting the structure to the structure network, and it is predicting the structure. So basically, the first level of information is it is taking 13 adjacent residues, 6 on the left, 6 on the right, and you can predict a secondary structure at the given step. In the output layer, for each residues, you have the scores for helix, strand, and loop. And at the second layer, it is the role of it is to include dependence on the conformation predicted for a residue and conformation of its neighbors. So it is taking prediction of all the residues from the first layer, and the second layer, it is kind of merging all the predictions together, and it is discarding all the predictions which are not possible depending on all the rest of the residues in the sequence. And the output layer will be similar as input, and it will give you scores basically based on if it is present in a helix or a beta sheet or a coil or whatever, right? So yeah, so just to summarize everything, so we have a lot of so protein structure prediction is basically something of was an open-ended biological problem for the past 60-70 years. There has been many techniques developed for predicting these structures, but as you can understand that similar sequences will give you similar structures, right? So if a particular algorithm can identify these patterns inside protein sequences, they are going to be able to predict the structures much better, which is actually deep learning models are doing, which is actually what AlphaFold and other deep learning models are also doing. So the protein structure prediction moved away. The field moved away from statistical predictions like these kind of predictions that I showed, Chow-Fastman, and other approaches like GORs and so on and so forth. It moved away from that to neural networks and deep learning, because it is easier for a machine to see a pattern and predict than humans, right? So it is easier for machine learning models and deep learning models to do that. So yeah, just to wrap it up, so most of the methods that we have discussed, so we have discussed Chow Fastman, we have discussed GOR and PhD, they are ranging from 50 to 70%. uh, and if you take a weighted consensus across different softwares, you get a better result, obviously. But I think AlphaFold 2 has a higher prediction accuracy than all of these methods. So yeah, that is the gold standard right now. Okay, so yeah, that is all from my side in terms of the discussion. If you have anything, you can ask, or we'll move on to the questions for this week. Okay, then we'll move on to the questions. I'll keep the questions on screen for a minute or so, and then we'll discuss. I'm shutting down my camera because I'm facing some internet issues. So yeah. So you have E and C. Okay, another B. Okay. Hmm. The answer is dipeptide composition. Right. I think we have not discussed this, but the idea is that when you are talking about residue pairs, you're looking at two residues at one time, right? You are quantifying the preference of amino acid residue pairs, not amino acid residues. So you're looking at residues at a point. So amino acid composition would look at individual residues. To quantify the preference of pairs of adjacent residues, we use dipeptide composition, which basically calculates the frequencies of all 400 possible pairs, 20 amino acids followed by other 20. So what are the possible frequencies for these 400 possible dipeptide compositions? So all of the rest of them are basically, so hydrophobicity profile and amino acid composition, it is based on single residues. But when you're looking at pairs, it is the dipeptide composition. Yeah, that is the correct answer. So the N flag, it tells you the word size, which is the Kmer size. Okay. Moving on. Do I have any answers? Not yet. Okay. I see a point one and A is point one. Okay. Wait for another minute. Okay. I have been given the answer to be point two. I am also not sure if it is point one or point two. Let me check. So many of you are saying it's point one. Okay. Sequences are correct. PLLT, KLH. Yeah. So you have two A's, one R, one H, one K, three L's. Yeah. One P and one T. Right. That is correct. Here also you have two A's, 0 R's, 1 H, 2 K, 3 L's, 1 P, and 1 T. Yeah. So I can see a difference in R here and a difference in K here. So it's 2 by 10. So the, is it like a lot of you answered point one? I'm curious to know, like, uh, how did you get point one, or like, uh,
Sir, I forgot to account the R because it was not present in the second sequence.
yeah. Okay,
It was a silly mistake.
you need to be careful about that, because in exams also these kind of questions probably will come. So, yeah. be careful about when you're doing these comparisons. Okay, moving on. Do we have any answers? Okay, wait. Do we have any answers? Okay, B1. Okay, I'll give another minute to discuss. Okay, again, I'm not sure how you guys are finding 0.56. Yeah, so this is basically the Chow Fastman method, right? So you're calculating the propensity ratios. So basically, what is the overall probability of the residue being in a helix, which is given 800 out of 1800, so that will be 0.44, and probability of alanine being in a helix is 440 out of 640, right? So that is like 0.68, and the propensity ratio would be this probability by this, so that brings to, oh, uh, 1.57. I think it is also scaled by log, if I'm correct. Uh,
Yes, sir, it's scaled by log. I got the answer 1.1.
okay. Just let me quickly check one thing.
Okay, sir.
Uh, Yeah, it looks like 1.01, but I'm not sure where the log scale is coming from. Uh, okay, I think this.
Sir, actually, we compute the 0.68 by 44 log and the propensity ratio.
Yeah, but I
I
don't think if you
think
take
so.
log of that, it comes as 1.01. So
No,
this.
no, no, sir. What I have done is that I have divided 800 by 1000, and then I have divided 1000 by 1800, which was, and then I took the division of
Uh,
0.44 and 0.55. Then I divided 440 by 640 and 200 by 640, which, and then divide these, the result of these two, and then took a log of these and uh, added them.
okay, okay. So I'm missing probably a formula here, which is taught. So
Yeah, yes, sir.
yeah, yeah,
I think so. It's available in the bioinformatics transcripts that was uh
okay, okay, okay,
given to us.
okay, okay, okay. So
But I'm not sure if it's the right way to do it, but I think so it's the right way.
okay, I have to get back on this one because I am not sure how this is done and how they're getting 1.01. I have to look at the formula and get back to you. I am not sure about this one. So uh, I'll skip this one. I'll come back to this. I'll take a note of this. This is question number 4, week 5. I'll probably get back to you. I'm not very sure if this is correct or not. So yeah, we'll move on. But I'll come back to this probably next week. Next week, if somebody can remind me once, I'll take a look and I'll let you know.
Okay, sir.
Yeah. Okay. And this is quite easy, I think. Yeah. So Avil and Neha, I'll get back to you in next class. I'm also not very sure about this particular question. I'll get back to you. This one is fine. This is like, yeah, D is the correct answer. So yeah, the lower the sequence similarity, the better it is for non-redundant sequences. So yeah, that's fine. Okay. Keep in mind the order. Psi is given first, then phi. So yeah. Okay. Yeah. Yeah, that's the correct answer. Psi is the alpha carbon and the carbonyl atom, and phi is the alpha carbon and the nitrogen atom of the amide. And by the way, carbon nitrogen is the omega angle. If you didn't know. Yeah, the correct answer is patterns. It looks for hydrophobic and hydrophilic patterns. If there is alternate of hydrophobic and hydrophilic, it is an amphipathic strand and so on and so forth. I think we have discussed this in enough detail. Yeah. Okay. Answers. Couple of ways. C. Okay. Okay, the answer is the third quadrant. Basically, if you remember this, so firstly, alpha helices are mostly right-handed. So there are, I don't think there are naturally occurring left-handed alpha helices, and these are your set of alpha helices here, right? And these are your beta sheets. So all your alpha helices are supposed to be in the mostly in the third quadrant region. So yeah, and almost all alpha helices are uh, right-handed. So between negative 60 psi and negative 65 and negative 45 psi. Yeah. This we discussed today. A and C. Okay, I'll wait another minute. A and C. Okay. Okay. Let me go back to this slide. Yeah. So, alpha helices has 3.6 residues per turn. 5.4 angstrom is the rise, which is the length of the strand in which covers one turn. So that is 5.4 angstrom, and the rise per residue is 1.5 angstrom per residue. So where did the question go? Yeah, the correct answer is basically the third option, 1.5 turns per residue. This is the rise. 5.3 is the rise, and rest of them are not true. Okay. Yeah. So 5.4 by 3.6, it's like 1.5 angstrom per rise. Rise per residue, sorry. So, yeah. Okay, moving on to the last question. Yeah, rise can be variable, obviously, but this question is not asking that. There, you can have left-handed helices, you can have slightly different alpha helical structures, but those are the rare ones. Like you won't find them like in 99% of the cases. In 99% of the cases, the alpha helix structure is fixed, right-handed helix, and those parameters that we saw for that. There can be variations definitely, as with different types of DNA. We have A DNA, B DNA, Z DNA, and alpha helix also has different types of helices. But yeah, that question is not for that. Yeah. Okay. I don't know what was the answer given by you guys. Let me check. Take a look. Okay, so C, a couple of B's. Okay. Okay. Let me just quickly show you. Yeah. So the torsional angle is with respect to the alpha carbon, right? So the psi, phi, everything, these are torsional angles, but these are with respect to the alpha carbon. So the question was how many how many minimum atoms are required to compute these torsional angles. So the idea would be that you need this, and the carbonyl carbon. So this is the psi angle, this is the phi angle. But to define this, you need the nitrogen atom, the alpha carbon, and the carbonyl atom, which is the carbon and the oxygen. So these four atoms are required to compute these torsional angles of phi and psi, right? So uh, technically we say the N terminal, the alpha carbon and the carbonyl carbon, but the carbonyl carbon is composed of two atoms, the carbon and the double bonded oxygen. So technically it is four atoms required. Okay. Yeah, so that's all from my side. If you have any questions. Okay, if no more questions, we'll close this session, and I'll definitely uh, old school alternatives are these kind of methods. We'll talk about more methods in the next few weeks also. But this Chow Fastman or this PhD method or GOR, these are old school alternatives to AlphaFold. But these are not very accurate in predicting. Because as I was saying, that the best way to predict is to see sequence similarity and homology and then predict on that. And machines and neural networks can do it much better than any kind of statistical technique that will do. So it won't outperform AlphaFold or similar algorithms, but yeah, these are the old school. We'll talk about more old school algorithms in the next classes as well. So yeah, the techniques that you are learning are all old school. So this bioinformatics course, if I'm not wrong, was taken in like early 2010s. So it is like around 2015-16 ka course. It is a little bit older course in that sense. So all the techniques that you are learning are mostly old school alternatives. These techniques are not very widely used these days, but the algorithms remain. The concepts by which those algorithms are built are still in use. We just have much more efficient ways of doing that currently. But yeah, so my advice would be to not disregard this set of softwares or algorithms, because based on these the next generation softwares or algorithms are built. So if you can understand these, this will provide you with a very good foundation of the understanding which you can use later. So yeah. Okay then. Thank you for joining. See you next Tuesday same time, and I've written it down for question 4 for this week. I'll try to get back to you. And if somebody can, please remind me next week as well during the class. Okay.
Okay, sir.
Yeah. Thank you.
Thank you, sir.
Thank you for joining. Yeah. See you.